try to get out. Okay, nice. So, welcome everyone to the second session of TruX Distinguished Seminar. So we have here Dr. Maura Pintor from the University of Cagliari, and she's going to present her work on discrete prompt optimization for secure Python code generation. And I think more generally, that she will talk about security of LLMs and agentic AI in code generation. I think that's a very big intro.
Thank you, Daniel.
Welcome.
Okay, let me share my screen and then I will start. Okay, yeah. Okay, so I'm very happy to present this work. As Daniel said, I will also touch a bit on other topics, mostly because my original expertise is actually on machine learning security. So actually attacking machine learning rather than security of things produced by machine learning. But you will see that we managed to incorporate some of my expertise also in this work. In fact, in this case, I'm trying to control the behavior of the LLM that produces code in order to have fewer vulnerabilities. So this is really the shortest summary of the paper I can provide. But let me start with what I said before, right? My expertise is in fact the opposite, right? So this kind of attacks in which you have any model, machine learning model, you can think of classifier that take as input images, but also any other thing where you have a machine learning model with parameters inside. And then in my everyday job, what we do is actually use some manipulation to the input of the model so that the model sees something else. In this case, we have, this is the first physical adversarial examples in which this guy with these colorful eyeglasses is usually seen by a person as a guy with colorful eyeglasses, but the machine learning model, because of these colorful eyeglasses, sees the actress Mila Jovovich. And why this happens? Because simply they are leveraging some weakness of the model, some spurious correlation that were picked up by the model during training, and then we are able to control the behavior of the model by manipulating the input that it takes. And there are other cases, this is a traffic sign example. We also have these manipulations in other domains. As I said, we have in the audio domains, you can add something to the waveform, and basically you can have whichever transcription you want. And I stress this as controlling the behavior of the machine learning model depending on the input, because this we are going to reuse this concept. We also have, of course, and I will come back to this, we have attacks that actually work on language models. So this is the first, I would say the first optimized attack that worked against the guardrails that are put to, let's say, delimit what ChatGPT and other chatbot like LLMs can answer to users. So you see here, it's a clear example. I'm sure you have seen people asking ChatGPT the instructions on how to build a bomb, destroy humanity, and something that the model is not supposed to elicit. But actually, the model will answer if you're able to find something that alters what the model sees. In this case, they were able to find this suffix that is disappended to the request of how to build a bomb. And because of this suffix, the model doesn't see it. I mean, the guardrail actually of the model doesn't see anymore the threat in answering this. Okay. I will describe it again later, because this is actually how you can manipulate LLMs in general on how to have whatever answer you want. Specifically, in this case, we don't want a malicious answer. We want actually to reduce the number of vulnerabilities. But you can have similar, you can craft similar things that still work in order to achieve the goal that you are optimizing for. We will see it later. Okay, again, just a little introduction for whoever is not familiar with this stuff. The idea here, as I said before, you can have whatever type of data here. Okay, let's keep it simple, and it's a classifier of images, and it can classify these three classes. When you train the model, what you do is minimize a loss function, and you change the parameters of the model, so these weights that we have here, in order to make the output of the model, so the scores that you get out of the model, match the true label of the classification, right? So you do this by changing the inner part of the model, the parameters. Instead, when you want to attack it, or we will see later what we do with this information, you still have an optimization problem. But in this case, well, if you want to attack the model to make the highest number of mistakes as possible, you just take a loss function that can be the classification loss function and maximize it. So you just decide that the model has to make as many mistakes as possible. But in this case, you don't change this. You don't change the inner part, but you change the input. So you are adding some noise or some artifact to the input so that the output will change. Okay? And you can see this as regulating the behavior of the machine learning model depending on something we have in the input, right? In our case, what we will do is define an optimization problem to solve our issue of vulnerabilities, and then manipulate what we have in the input, that is the prompt, in order to reduce the number of vulnerabilities. So in general, this is the case. What's cool about this is that the model is fixed. So this means that we can do this. We can reduce the number of vulnerabilities that are outputted by the model without fine-tuning, without changing the parameters. And this is good because the parameters of these models, we cannot touch them. We cannot usually train ChatGPT or train DeepSeek because they are huge models. But what we can do is provide some additional input that regulates the behavior in a good or bad manner, of course. Okay, and the application we are talking about is not recognizing parrots, but it's this kind of application that I'm sure sounds familiar, looks familiar for many of you. In fact, at the moment, I believe the most common use for software science, for computer science of LLMs is an LLM integrated inside the IDE, so your software development kit, and it is just there, and you can ask questions. You can ask, for instance, write a function to say hello to the user on a web application, and then the LLM will take this, that is the task that you are giving to the LLM, and create some code, right? Generate some code. I will not go deep in the how it is produced. Of course, it is using autoregressive, an autoregressing function, so it will generate token by token and so on. But for what matters to us, let's look at this model exactly like as a black box, a big box of parameters, and then we only observe the input and the outputs. This, again, it's not because we are not able to do that. We can also look internally at some of the models that are publicly available, but we want to use the huge power of these big models. And in general, we don't have access to the loss function or to other things that we can do inside of these models. So we will just look at what a regular user would see, right? So the generation, you can ask things to the model and get the outputs. Now, what is the problem with this beautiful IDE integration? It is that these models actually learn very well how to produce vulnerable code. In fact, in this slide here, this is taken from a paper that I cited in the slide. You see the first block in the top is the requested by the user. The green part, focus on the green part, function which says hello to the user. Now, this is something that everybody is supposed to know how to do, but let's, for funsies, ask an LLM to do it. And you see the first, I mean, these are three possible solutions. It's the first one, the highest ranked. It is just doing the things that are written in the in any documentation, do the simple thing. What is the problem with this? The problem is that this username is passed inside an HTML template, and it's controlled by the user. This creates a vulnerability because the user can also inject some JavaScript. And when this HTML page is rendered in the browser will be able to run some code, will be able to run some JavaScript if the user is able to inject some JavaScript inside of this username. So instead of using it in a benign way, we mess with the code written by the whoever wrote this code, and then the user will be able to run arbitrary code. This is super dangerous because you can do very bad stuff with running arbitrary code in some web server that is providing this functionality. Interestingly enough, the fourth highest score, so the one that the user wouldn't even see, wouldn't even look at, is the safe one, where there is this escaping. So there is something that removes any possible injection of, I mean, not any possible, but all the known ways to inject arbitrary code. Okay, so this is why we need to focus on this, because actually there is a chance that the highest ranked code, it's not definitely aware of the security implications. Okay, so this is because by design, in training, the LLM was not told to be security aware. Okay, any model is just looking at code in GitHub and learning as much as possible how to generate it. Then security, that comes as a not even a requirement, it's just a counter effect of whatever I'm using. The other thing that I want to stress is that you can also tell the LLM directly to write secure code, right? This is incredibly not easy to do. We tried, of course, we tried several different prompts where we mentioned the word security, we mentioned be aware of this and that, but it's definitely, it requires a lot of work. And usually, you know, developers that are not trained to be security aware can also, it's difficult for them to understand what they should ask to the LLM. So the idea we had was, what if we can find a universal prompt or some sort of automatically tuned prompt that is able to reduce the number of vulnerabilities for all the possible tasks, or in general, to generalize well to a set of tasks. So in this case, as I said, we define everything as an optimization problem. And don't be afraid of the math. Okay, let's start from the top. First of all, we define what we are asking to the LLM as a combination, actually a concatenation, a simple concatenation of a prompt that is generally describing the task. It's generally describing the request. And then the task is actually the description of what the LLM has to implement. So in the first part, you can imagine write a piece of code for implementing the following task. This is just a prefix to the task, that is write the function to authenticate the user, or write the function to say hello to the user. Okay, so the task is the specifics. The prompt is actually just a prefix. Okay, it's and you might think this doesn't have a lot of influence on the output of the model, but actually it does, because it's all about how you ask to the LLM. And then the third ingredient we need is a scoring function. That is our objective that we're trying to optimize. In this case, our scoring function is, let's simplify it for a bit, and then I will go in the more detailed one. But in general, you can think of it as the number of vulnerabilities that are produced by the LLM. So you have a sort of a number that is higher if the code is bad and lower if the code is better, right? And then you can just have a bunch of prompts, try them, and get the output of this scoring function. And if it's reducing, you have a direction to follow. You have some prompt that is better than the other, okay? So this creates some automated optimization. Now we're gonna use some sort of algorithm that is very intuitive in our work, but be aware that you can put any optimization algorithm that solves this. We start with a generation function that is basically our model. So this we cannot change G. We can change P, that is the prompt, the prefix, and then X. Actually, we don't have. We decided not to change it. So X is fixed, and it's the stuff that we have to implement. So we cannot move. We cannot ask differently. Okay, this is a sort of a simplification, but think of it as what the user would input directly to the code ID. Okay, the prefix instead is something we can provide as a system prompt. So we can provide it even without the user typing it. We can write this part before the user request. Okay, and then we can generate a collection of code snippets generated by providing the prompt and the task. And then our optimization problem becomes find the prompt, so the prefix, that minimizes the scoring function, given that you can try all the possible prompts. Of course, all the possible prompts is an ideal situation. In our case, actually, we have several things to take into account. First of all, we cannot try all the possible prompts because that would be computationally very expensive. And the prompts are discrete, so we cannot increase or decrease like they are numbers, but we can actually change something in the prompt, a variation, and check if the scoring function is decreasing or increasing. So these are the optimization prompt. If we are able to solve this exactly, we are able to find the best possible prompt. We are not able to do that, but we can leverage solving algorithms to get as close as possible to the solution, to the true solution. So we want an algorithm that is able to, by looking at the input and outputs, to optimize in a black box manner. Black box means that we are not able to look into the parameters of the model or whatever. And this is naturally working actually in genetic algorithms. Genetic algorithms are some sort of optimization algorithm that was used also successfully for creating adversarial examples, I want to point. But they are very easy to understand. So you have a population of prompts. In general, it can be a population of anything, okay? A population, and then you have this fitness score that ranks them to based on how good they are. In our case, we have a natural way of measuring. It is the scoring function that I mentioned before. So for instance, the number of vulnerabilities. And so we can have this generation, rank them by the number of vulnerabilities of their outputs, and then select. So we just remove the ones that are not promising. After that, we have a set of candidate prompts that are better than the others. What we do with them? We make them mutate. So we take those initial possible solutions and we change something. Then we have a new population, so we can rank again and create this iterative process that selects automatically, but without us training any model or without us inspecting the internals of the models, creates a ranking of the possible prompts. And well, if you iterate several times, then you might get better prompts than the originally defined ones, so the ones in the initial family of prompts. Okay, and then that's what we designed. Actually, we designed this loop. I will divide it into the phases. The first one, you prepare a bunch of prompts. So you have these seed prompts that enter the scheme. And these are manual prompts. So you just have a few guesses on what a good prompt can be. Or you can, I don't know, ask an LLM to generate them as you want. You put them into the system, and then you query the LLM that creates the code from these prompts, code snippets. Now, there is a little step here that I will not comment too much on it, but you have to also ensure that the Python code, in this case, we focused on Python. Of course, this is generalizable to anything else. You have to ensure that it's valid code that still runs. Python is an interpreted language, so this means that you have to actually run it, or to run something that is able to understand if the code would throw a vulnerability or some sort of error. But you can at least have some automatic checker. But we also manually validated the code that was outputted from these LLMs. Then you have the scoring part, where we used a static analysis tool that is called Bandit to produce the vulnerability analysis report. So this is just a static analysis, pure static analysis, that pulls out a list of vulnerabilities that are present in the code in each of these snippets. Plus, it gives you also some other information, for instance, the severity and the confidence of the found vulnerabilities. This is useful because you might be able to solve all the weak vulnerabilities, like something that is very difficult to exploit for an attacker, but leave a huge hole in security if you leave a big vulnerability, so a high severity one, like the one I presented at the beginning, where the user can inject code inside the rendering function. Okay, now you have this, you compute the scoring function, and you get the top K prompts. So this K is what selects the best prompts available. Mutate and rinse and repeat for TI iterations. And then, as output, after TI iterations, you will get the best prompts you could find with this process. Okay, so it's a very simple optimization algorithm that is trying to solve the problem we had before. The problem we formulated before. This is about the experiments. I think the notable stuff here is, well, first of all, the dataset that provides some coding tasks. Again, the tasks. So what we are going to request to the model, whereas the prompts we wrote them by hand. And you can see that they start from a very simple way to more complex requests. And they kind of mention always the word secure, just because we want to be optimistic about it and think that the developer or any system will just use this word. And then from this, we generate code with these 5 models. They were state of the art at the time. Now, there are better models, definitely, but the same process can be applied. So this is really beyond what we could test, but we still have some interesting results on these models. And the scoring function, as I mentioned, is something that we combined everything that comes out of Bandit, the analysis tool, in a single number. So you can optimize over this single number. And it has a multiplication of the severity and confidence. So how bad is the vulnerability times how likely it is true that there is this vulnerability in there. You're never sure unless you test it on your own skin. So confidence is something that the model spits out, that the bandit tool spits out, and you have it as an output. Plus some combination of terms that balances the number of vulnerabilities that are implicit in the creation of code and so on. So this is just a minor thing detailed in the paper. Okay, mutation mechanisms. Want to not to go too much in detail, but we use some generic technique. Generic means what I would use even if it's not code. So for instance, you can use back translation. Back translation means I translate on Google Translate on another language and then translate again to English. Paraphrasing, you can guess. And then the other two are actually more security aware. The first one is self-guided. It is just giving the code to the LLM, to another LLM, and refining and telling the LLM to make the prompt in a way that makes the source code more secure. So no analysis tool is involved in here. We just pass the output and tell the LLM, this looks not secure. Please make it more secure. Feedback guided instead involves Bandit in the loop. So it involves the outputs of Bandit that we pass in the prompt when we request how to improve our prefix in the loop. So we are able to feedback guide the generation of the new generation of prompts. These are the results. I want to focus on two things. First, this is a very good indication. The plot on the bottom left is a good indication that the score is decreasing. So the number of vulnerabilities times the severity and so on is decreasing. And this is good. It means that our objective, as we defined it, is being reduced. And on the table, it's a huge table, but I highlighted the column density, that is the number of vulnerabilities per line of code. So it means that if I have a huge, I mean, it's divided by the number of lines the LLM wrote, and this is sort of telling you how many vulnerabilities are in general produced by a model. And the top number is the baseline, so the initial prompts without any optimization process. Whereas if you go down one step, and you can see it already improves in many of the cases. Of course, nothing is guaranteed, but in many of the cases, if you have the generic, only the generic changes, the generic mutations, so the ones like back translation and paraphrasing, you would have an improvement in the density of vulnerabilities. Whereas in the complete version here, we allow all the possible mutations, and then the process will select on its own the top candidates. So in this case, it also includes the security aware, feedback or no feedback. And this improves further the quality of the code that is, I mean, not the quality, but the density of vulnerabilities that are found by Bandit. I stress this, the vulnerabilities that are found, because there is a threat to validity to this. That is simply that the models are learning how to hide the vulnerabilities better. So this is still, I mean, it's implicit in the things that we did, because we are optimizing a function that is just a number that comes out of a tool. And if this tool is becoming worse because the LLM is obfuscating the vulnerabilities, this we are not able to tell. And this, of course, is something we assumed when we designed the process. The solution to this would be to use more vulnerability scanners, and of course also involve a human in the loop, rather than to check whether there are vulnerabilities, to check that the code is very readable and that it's not hiding something like obfuscation or some secret technique to hide the vulnerabilities from Bandit. Another thing that I want to mention is that if you keep the process going for too long, so if you have this mutation process over 20 iterations, you kind of lose sense. I mean, the prompt loses its meaning. As you see here, we have that after some iterations, and this happens also if you translate some text over multiple languages and then come back to the same, to the original language, you will see the sentence is completely different. And this happens to prompts as well. So you can imagine that it's losing the meaning, the human meaning, then probably it still works. And the security aspect. So it was not mentioning security anymore. Unfortunately, well, you see, after iteration 6, there is some sweet spot in which the text is not human readable, but the code is still produced, and it kind of works. However, as you lose meaning in the human value style metric, you also lose meaning in what the LLM outputs. So it's really not getting the task anymore. Okay, so this is sort of a side note that I want to point out. And I would say it is also possible to embed all this stuff in the next generation of prompts. So you can also include, we didn't do it because it's computationally expensive, but you can optimize over all the objectives jointly. So you can also improve the quality of the prompts that you get for being more human readable or for being security aware and so on. What changed since then? Because this was a paper we published at the beginning I mean, we worked on it for several months, but mostly a lot has changed that actually still makes it valid though. Now, instead of having just LLMs, we actually have LLMs that are able to call some tool. So to actually call functions that the author or the creator, the designer wrote, and then get the results back and put them in the loop of reasoning. So in fact, what we implemented was mostly an AI agent with the tool access to Bandit, and then providing the feedback again. But now this has much more freedom, because actually you can have also, the LLM reason about what to ask to Bandit. So it's actually even better if you think about it. So nothing prevents everything from working on a Bandit in the loop kind of manner. So this is still compatible to LLM, to AI agents. And another thing I want to mention with AI agents is the protocol they use to work. I mean, this is the common one. Then there are other sub-protocols, but this is the one presented by Anthropic, where they implemented some way of making the agent, so the LLM, communicate with the tools. And the way they do it is actually by providing this communication language, where you specify the resources, that this can be, for instance, the IDE and the software that you're working on, so something that the LLM is supposed to process, the tools, so this can be Bandit, for instance, and the prompts. The prompts, it is exactly what we are optimizing. So you can actually specify a prefix to add to the request so that you can have better results. So in this case, it's still perfectly compatible, and I think it's a good solution that we can actually also embed into more complicated systems than just having an LLM doing input and output processing. Now, some limitations of this work I already mentioned. First of all, it is model specific. In the paper, you will see that if you optimize the prompt for one specific LLM, it doesn't work as well to the others. So you will have to incorporate the LLM in the loop. And if you change the LLM, you will have to find a new set of prompts. It is solvable in some ways, and actually in the paper where they attack the guardrails of GPT, they do it by simply incorporate multiple models. So you can have an ensemble of models that is involved in the optimization, and this improves what we call transferability. So it means something that works on a model to change the behavior works also on another model. The fitness scoring depends on the tests that are run on the LLM output. As I said, if the LLM is producing some code that is not being possibly scanned by Bandit, so there is no test to check for this vulnerability, or the vulnerability maybe is not yet found, we don't have a guarantee. But of course, this is something we have to accept. We never have guarantees when we test the source code for vulnerabilities. However, this optimization process can become better in hiding those vulnerabilities. This is something interesting that can also maybe stimulate the minds of people in improving vulnerability scanning and finding stuff that was not yet found in the CVEs that are available online. The rest of limitations, I mean, of course, this is a continuation. The security evaluation metrics may not capture all vulnerabilities. And it still involves some human in the loop in this case, because we were manually validating some prompts. For instance, in these plots that we had with the number of iterations, we manually validated that the number of iterations after a certain point makes the optimization objective lose its meaning. Now, as future improvements, as I mentioned, we can have AI agents optimize these. So you can have not only one single agent, but you can also have several agents that reason about how to make code more readable. So maybe one is in charge of writing the code, and one is in charge of evaluating the code, and one is in charge of proposing the new prompts. So this can be done in a multi-agent setting. Then, as I mentioned, you can also optimize for several metrics altogether. So to make the code more secure, but also correct, highly performing, so efficient, more readable by humans, or even better, by the testing tools. So this testability stuff that I put here can be an objective. So the number of lines of code you tested for vulnerabilities might improve. So this is also something that I'm really interested to see, how to improve the access that the outputs of LLMs, I mean, how to improve the ability of tools we have to inspect code that is not written by humans anymore. And the transferability aspect, I already mentioned. You can find a universal prompt that works for all the possible models you might have. But this is kind of niche, because in general, when you adopt an LLM to write code, you don't often switch. So usually there is a company policy, for instance, where they decide and agree to use this LLM, and that's what we are going to use. So this is less interesting, but still interesting on the research aspect, I believe. And that's it on my talk, but I'm happy to take some questions now.
Yeah, sure. Thank you so much, Maura. Thank you. First of all, I requested your LinkedIn. Please add me on your LinkedIn. So yeah, but to Maura, I think I have a lot of questions, but maybe we should open the floor to other people first. I have like 4 questions here, because we actually actively working in this direction. And we're also really privileged to have Batista last week as well. So it was a really good time with him as well. But I want to open the floor to anybody, and maybe those online as well. In case you have questions, can you please just unmute yourself and ask before I bombard my questions? Yeah,
I'm sure then you have already seen the first 2 slides I presented.
Right.
Batista.
So it was a very good refresher. Really lovely. All right. So Melissa, please.
Yeah, thank you so much, Emmanuel. Thank you so much, Maura, for the very interesting talk. I have some questions. I'm wondering, like, since the initial prompt, like maybe the final prompt, like the optimized prompt, is a bit far away from the initial prompt, how to be sure that we're not going far away from the user requirements in the initial one? So this
Yes,
is the first one.
So the idea is that these prompts are system prompts. So imagine the scenario in which I have the agent here. So I will maybe what the user will see is this chat here where they have the task. They can describe the task, so implement this stuff given the code that you see. But the prompt we are optimizing, it's what we control. So who provides the agent, for instance, who provides this, will put this prompt before the user request. So this is one thing that is important to know. And the other, of course, if you look at the final results here, if you have a prompt that is too far away, there is a risk that the user will not, like, whatever request they use, they put, the request will just diverge, will just not do what the user wants. In this case, I would say there is no yet a solution unless you have either some human in the loop or some LLM in the loop. But these are like I don't like it that much because the LLMs also have a tendency to take shortcuts. So if you put two LLMs in combination and one has to evaluate the job of the other, it's more likely that they will learn to cheat rather than to actually produce some meaningful stuff. So this is something that I think needs to be taken into account and manually inspected after you do the optimization. I don't know if that answers your question.
Yes, thank you so much. But like, a bit confused. Like, are you like when you're asking the agent, are you gonna give the optimized prompt as a prefix to? Yeah, that's
Yes.
it. Okay, okay. Thank you
Yes,
so
this
much.
is actually, I don't know if some of you have contributed or have tried to do some challenges, like where you have to jailbreak an LLM, for instance. Usually they have a system prompt, so they instruct the LLM, oh, this is a security challenge, don't give the user this information, and then they put a lot of instructions. Okay, this is the system prompt, and then the user has to break into the LLM, so they have to convince it to ignore the previous commands. So it's similar to this. It's some hidden prompt, but still we want to be able, first of all, to read it, because otherwise there is a chance that actually it's making everything worse. And then to, force the user not to manipulate that, but that is beyond, like, you have to assume a benign user in this case. So they are not messing with the system prompt.
Okay, thank you so much. Another question that I have is that like you're using feedback guided by Bondit, and then like for the loop and the refinement of the prompt, and then the output, like you're measuring it with the same static analyzer tool, right?
Yes.
Isn't there a bias, like it's
Absolutely.
optimizing for this security analyzer?
Yes. In fact, I don't know what happens if you change the security analyzer. This is something we didn't test.
Yeah,
But
yeah, since we worked on this, and we noticed that if you change the static analyzer or you're using several other scanners, the security like collapse a lot.
yeah, this is a good point. I believe the best choice is to use several security analyzers. Like 3, provided that there are 3 good security analyzers, and then use the leave one out approach. So test on a different one.
Okay, so for the analyzer, you're proposing the static ones, right?
Yes.
Okay.
I mean, you can also do it with dynamic analysis, but I believe the dynamic analysis also introduces a lot of noise and a lot of computational overhead.
Okay, thank you so much. I think that's it for me for now. Thank you so much, Maura.
Thank you for the questions.
All right, so I see Elassine. Elassine, please. Yeah, awesome. And thank you so much for turning on your camera. Melissa is currently not feeling fine, so that's why. So please, if you want to ask questions online, please turn on your camera so we can see you. Please, Elassine.
Thank you, Maura, for the nice talk. Actually, I have a question related to the evaluation part. My question is about if, for example, the security analysis is done on a standalone function, for instance. For example, that is maybe the function itself as a standalone could be vulnerable, right? Because you have maybe an input, but in general, this function is integrated in a program, a whole program, right? And we did the control somewhere else. Maybe even the function access is private, right? In this case, one will never happen. So did you, in your evaluation, consider maybe patch data sets, or the function itself generating something in a whole big program, maybe to test and see actually if these security issues still come across when they are integrated in a coding context?
Maybe if I can ask to repeat the question. So just let me know. Let me know if it's good what I understood. So you mean the code that runs the agent is vulnerable?
For example, I'm talking more about the data set. For example, if it's the data set of functions, right? And the LLM itself, is generating a prompt to a function, for instance, right? So this function, if we analyze a function as a standalone, right, we take the input and say this input goes prompt injection, right? But in reality, most of the cases, we don't generate just a function, right? The function is called in a program, a part of the program. So it will be maybe interesting to evaluate how the LLMs generate function in a full program and see how vulnerable it could be.
Of course, yeah. For dataset reasons, because collecting a dataset with full repositories and so on, it's much more challenging. But it is a good point. So, and I think this is enabled by the use of agents inside IDEs, for instance, where you have to look at the entire code to make a sense out of all the possible paths that the program can take. In our case, we were looking really at single function vulnerabilities because this is not yet a solved problem. So of course, if you have a vulnerability that is in a single function, it's highly likely that it can be exploited anywhere. Of course, even if you encode it in a bigger repository, but we didn't actually look at more complex repositories. This is some work it can be a future work.
Yeah, actually, yeah. But what I wanted to emphasize here is that most of the functions, like we do not handle the inputs. The inputs are handled somewhere else, right? For example, we have a main function, we call different function. So we first handle the inputs before even calling the function. For example, hello, your name. So here, your name, I can handle the input before even giving it, right? Kind of before, so I can treat it somewhere else in a big program instead of just having a function.
Like this escape function can be somewhere else in a different function.
Yeah, exactly.
You mean this? Yeah, of course. No, this is something we didn't expect. Yes, it's focusing on a single function. Of course, it is true. However, it's kind of risky because then you have to trust that you will not use this function anywhere else. Whereas maybe the LLM is not aware of it, so it will reuse it somewhere and not escape it everywhere. So in general, I would say it's a bad practice, unless, but I don't know. I might be wrong. I'm actually more expert in the machine learning part than the security part. I would say that adds some context. So you can also, provided that you have tools that are able to do this, you can also inspect that as well.
Okay, that's all for me. Thank you.
Thank you.
I do have a question. So first of all, just to see if I understood, basically the idea would be if like, okay, there is like a system prompt in many, basically there is also like on online tools, GPT have, Claude, I think, was, let's say, stolen, or let's say there was like a leak. So in the system prompt, the idea is when you use an agent for coding, you can have a prompt in the beginning, which should be still somehow human readable to avoid, let's say, that some cheating, which
Yes.
improves security, and that you optimize through reinforcement learning, basically through it's not reinforcement learning, but it's optimization of
algorithm.
genetic algorithm in this case. Now, I have a couple of questions. One is the how task independent can the, let's say, the encoding be, as in, sorry, not the encoding, how task independent can the optimization be, as in you optimize, like an agent in the end would work on many data sets or on many types of function, many languages, whatever. I assume that in principle, the optimal solution, if you just optimize, can be different. But I also imagine that you would like something universal, because otherwise you risk overfitting. Like, how well did you see the transfer among tasks? If you had any variation in the data?
It is all about what you include in the optimization. So if you, for instance, optimize over several possible tasks, where the prompt, like the tasks are fixed, but you have a batch. And then you can have several candidate prompts for each of them. And in fact, this is what we did. So 36 coding tasks for optimizing, and then we evaluated on 114. The prompt is the same. What changes is the task. So the other string that you have. It's similar to the process of adversarial patches. So I don't know if you have ever seen this, but it's they optimize to have an adversarial small square that you can print around and print and use around. And what they do is optimize over variations. So they optimize over rotation, size, and also the background. So I can use this patch to make myself being classified as a I don't know, a banana, or a notebook to be misclassified as a banana if I put the notebook on top. They optimize this just in the same manner. So they put several different images, then several transformations of the patch into the optimization. So if you include, for instance, different languages, even different languages, meaning that it's not necessarily English, you can put all the variations that you can include, they will be promoted with the genetic algorithm. So we didn't actually put many languages and other conversation languages, but you can technically do it.
Okay, and quick question. Do you think it's possible in agentic AI to basically have the brain, if that's the right tool, computing itself the prompts for the tools it uses, for instance, for coding, or is it again from two LLMs and then you basically get something unreadable and overfitting and whatever?
Yes, it's definitely possible. In fact, I think the easiest way to break an LLM right now is to use another LLM. So I think this trend going on recently that, I've been used to these kind of attacks in which to get this perturbation here, you would use the gradient. You would use something that tells you how to change the input, fine-grained changes, so that the loss changes. Okay, and this is for a classification model. It just costs you a backward pass, and then you can add the input, and that's it. That's the adversarial example. In new models instead, well, for instance, in the GCG, this one, you don't have this nice fine-grained gradient. What they did was a greedy optimization. So similar to what we did, change token by token and evaluate the scores. The way they create the mutation is slightly different, but it's basically the same thing. So it's already a shift between creating end-to-end differentiable attacks and this that is more expensive. And it's incredibly expensive. So if you run this attack, this GCG, universal and transferable, blah, 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 you will have 1 month of computation for just creating that string. Then it can generalize and it can work on different prompts and requests and so on. But it's a long running process. Turns out that you can have a similar effect if you involve an LLM in the loop. So ask the LLM what are the other candidates. And it works better than doing this greedy process. So instead of using optimization algorithms that actually find the gradient and find what's sensitive for this model, you will use something that creates a similar representation and ask for this thing that is able to understand also the spurious correlation of the data and so on to create a better prompt. So I definitely think the best way to do it would be to involve an LLM. However, there is always the risk that I mentioned before. So if you have two LLMs communicating, they might use some sort of steganography. And don't be, I'm not talking about complex theories in which they start talking their own language to conquer the humanity, but actually it's a stupid thing. They will exploit some spurious correlation or some communication strategy just to reduce the objective. So they will say, the easiest thing is not to make the code secure, but to convince the human that it is secure. And so they will just collapse in this optimization. This is something I criticize in all the approaches that use LLM as a judge. So where you have some task that is evaluated by an LLM, and you put that back as a feedback in the optimization. So this is always a risk. And it's again, it's not something about strange theories of AI taking over the world. It's just the way we made AI. It is optimizing, and the AI will learn how to use the easiest possible path, the path of least resistance. So it's it's an interesting thing to look at into now. This communication between agents and putting agents in the loop for optimization. We still have to figure out if it's a good thing.
Okay. Awesome. Any other questions? Yes.
I was wondering because right now the kind of the search for the optimization algorithm, it's kind of reminding me more like some kind of like grid search, where you just try a range of different prompts and then you choose the best one, right? With the feedback guided one, I think it becomes a bit more kind of directional. But I was wondering if there's any ways, that work on black box models, but that are a bit closer to, let's say, like gradient descent, where you because now, you get this feedback, but still, I'm not sure as a human, let's say I try one prompt and I get feedback from the static analysis tool. I still wouldn't really know what to change in the prompt, right? With gradients, you would know exactly in which direction to go. But
Yes.
like this, you don't know. So I'm wondering if there's a way, you try to use synonyms or some token or some words, for example, and then you see, what this changes, and then you might get to like quicker to the best or the locally best combination. Maybe.
So yes, one thing that I didn't mention is actually, so the problem with what you said is in this case, because it's an image, it's end-to-end differentiable. So it means that from this, that is the input layer, I can go back to the original input. So I can go back to the image. But let's say this is not an image, but it's text. What happens is it's split into tokens, and then you have these tokens here. Okay, so you can get the gradients up to the tokens, but then you don't have a mapping that maps every possible value, because this is sort of a dictionary of possible tokens. You will not be able to map to natural language. It will be numbers, and then it is a sort of a projection that is lossy. So you don't have a direct mapping of all possible tokens. So what they did in the GCG attack is actually, let me see if I have the slide here. Yes, they use a sort of candidates. You see, they want to optimize this suffix here. And they have several candidates that are projections of these tokens, the closest tokens to these that would change the output of the model the most. And so they do this sort of candidate extraction with some sort of gradients, but it's not that good. So you need still several iterations. And it's more expensive. I believe it's even more expensive than what we did. And yes, it works. It's still incredibly expensive. So I would say the best strategy is not this one, is not the other one. But if you were able to add something to the internal parameters of the models, so if you are able to add some sort of direction to this, so that the model changes behavior in general without fine tuning, you just find something to add to the parameters. This if you have a white box access and you can change the parameters. And this is called steering. They are doing it for enforcing guardrails, for enforcing harmful or harmless behaviors. So just changing the numbers that are in these matrices of numbers so that the model in the end picks up a new direction, okay? So this is probably more promising, in my opinion, than using end-to-end differentiation.
Okay. Okay. Thank you.
All right. I think there won't be any questions anymore, even if you have your questions. But I have one quick question. I think you were able to answer at least one of my questions 3 months ago, but I'll just ask one, and maybe I'll send you the rest on LinkedIn. You mentioned a point on other than kind of obfuscating the vulnerability. Can you explain what that means, like in details? Because I mean, now everybody wants to generate code with LLM, and if they're actually doing that, then what are we up to?
Yes, so it is actually something that happened also in the adversarial machine learning world, where you have these solving algorithms. They are able to find this perturbation very efficiently. Okay, so the thing that happens is that you will have the easiest tool will find it. So what you can do is actually make the model more complicated so that you hide this perturbation that is still there. It is just more difficult to find. The problem is when you evaluate.
It's difficult to find by the static analyzers, or is that
by the algorithm you are using. So I'm talking now about any vulnerability in code. You have a tool. If it's not able to find it, you have zero guarantees because it depends on the tools you use. And this was found also in adversarial examples. So we have evaluators, we have algorithms to find them. But if you make the model super complex, there is a chance that you will run the algorithm and it fails. You don't have guarantees that the adversarial example is not there. Okay, it is just you're complicating the test rather than actually making the model more secure. Because the way to make the model more robust would be to change the boundary, not to hide the stuff. And this is the same with the vulnerability analysis. You can run all the tests you want. You can also use human inspections and whatever. But if nobody is able to find the vulnerability, you cannot guarantee that there is no vulnerability. And this is why we have all these updates in libraries and stuff and code on GitHub and so on. They find the new vulnerabilities and they patch it. And it is mostly a reactive approach. So this is why I also mentioned that maybe we can also take inspiration from this, because if we make the models, let's say you have an AI model that evaluates these vulnerabilities. If you make it able to find vulnerabilities that are not found yet by the tools, this is even better. So we can also reuse some sort of research to optimize the code, to make it more vulnerable. And then maybe it will be able to find vulnerabilities that are not detected by but this is like a complete different view of this work.
Right. But just to clarify, you were making the example of obfuscation, right?
Obfuscation, yes.
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 Okay.
Awesome.
Obfuscation,
All right.
so we call it gradient obfuscation in adversarial examples, but it's called obfuscation in cybersecurity,
Okay,
and it's
okay.
a common thing in vulnerability analysis when the
Okay,
people
thank you.
just want to hide the vulnerabilities.
Okay, thank you.
Yeah, we really enjoyed the talk, but thank you so much. We have to go now because we have our meeting, but thank you so much. It's such a great joy, and please remember, add me on LinkedIn and we'll continue. Yeah, thank you.
Thank you.
Awesome. All
Thank
right,
you so
thank you
much.
very much. Yeah, sure.
Thank you.
Bye-bye. Bye.
Bye-bye.
Thank you. Thank you very much.